Hello, everyone. Thank you for taking your time to join us today for this exciting webinar being brought to you by Scintica. My name is Gabriel Escalante, and I will be your host for today's webinar. Our webinar today is entitled Introducing the IVIM Intravital Microscope. Today's webinar will be given by Dr. Sarah Rapich, Product Manager within the Imaging Division at Scintica. Sarah has received extensive molecular imaging training in Europe and Canada since 2008. She holds a master's in science in molecular imaging and a PhD in medical sciences from the University of Antwerp in Belgium. Her doctoral research focused on the evaluation of novel radiotracers as biomarkers of treatment response in colorectal cancer model using nuclear imaging technologies. During her postdoctoral fellowship at the Princess Margaret Cancer Center, in Toronto, she studied the complex tumor microenvironment of pancreatic cancer using intravital microscopy. During this webinar, Sarah will introduce the fundamentals of fluorescence microscopy, review some example images, and focus on this technique's intravital imaging applications. As some of you may know, Scintica is a distributor of IVIM's intravital microscopy platform systems here in North America. Today's webinar is the second in a four-part series, which will be spread out over the next few months. Please keep an eye out for emails in the coming weeks with additional information about upcoming webinars, or simply visit our website to watch our previous sessions. Before we begin, I'd like to briefly mention a few housekeeping rules. We anticipate that today's presentation will be just under an hour, so we may not have time to answer your questions live. However, please feel free to submit your questions to the Q&A dialog box throughout the presentation, and then we'll work with the team to get them answered. We will create a transcript of the questions and we'll distribute this document within the next week or so. Please also note that we are recording today's session, so if for some reason you lose your connection or can't hear everything clearly, you will have access to the video file to review later. Without further ado, I'm going to pass things over to Sarah.
Thank you for that introduction, and thank you to all of you for participating in this webinar. I am very excited to introduce you to IVM's technologies all-in-one intravital confocal and/or two-photon microscopy system. I'll kick off the webinar by giving you an introduction to intravital microscopy, and then I'll spend the majority of the time giving you an overview of the IVM systems and their capabilities. Then we'll wrap up with some key research applications of intravital microscopy, showing you really nice images obtained with the IVM systems. Let's start with some basic principles for optical and fluorescent imaging. When comparing preclinical imaging modalities, the parameters that play a large role in choosing the correct one for your research are spatial resolution and penetration depth. The general rule of thumb here for any form of imaging is that the maximum depth you can reach is about 10 to 100 times the spatial resolution of that method. In this chart, I've delineated the optical imaging modalities with the orange square, and you can see that while they have the best spatial resolution, reaching micron level, being able to image cellular structures, they have the poorest penetration depth, with microscopy only reaching up to maximum 1 millimeter depth. The reason for this poor penetration depth in vivo optical imaging can be found in biomolecules in the tissue through which the light travels. More specifically, the hemoglobin found in oxygenated and deoxygenated blood will absorb light maximally in the lower wavelengths, meaning the blue, green, yellow wavelengths, while in the higher wavelengths above 1,000 nanometers, which will be in the infrared range, water actually becomes an absorber of light, contributing to the low tissue penetration depth. This means that the optimal imaging window for in vivo optical imaging is in the orange-red wavelengths of the visible light spectrum and the near-infrared wavelengths, meaning between 600 and 1,000 nanometers. This is important to know when selecting fluorophores in fluorescence imaging, since the fluorophores have to be excited by distinct wavelengths and will emit at a distinct wavelength as well. Fluorophores found in biological tissues can originate from any of these four sources. They can be genetically modified fluorescent proteins, ranging from blue to far red spectrum. They can be organic dyes, such as the green FITC and the red TRITC, which are typically used for vasculature imaging in vivo. Or they can be any of the Alexa from the vast range of spectrums there that are typically conjugated to antibodies. They can be from inorganic dyes, such as quantum dots, or fluorescence can originate from endogenous species, such as elastin and collagen, and the metabolic enzymes NADH and FAD. Here, essentially, you're imaging autofluorescence originating from these species, as you're exciting them with the correct wavelength. Besides these, the fluorescent proteins can also be expressed endogenously if you transfect your cells or even your whole mouse with them prior to imaging. Otherwise, fluorophores are typically introduced externally, and in vivo, this is typically done through injection into the bloodstream. Overall, the use of fluorophores makes fluorescence imaging very specific and sensitive, and allows for imaging of dynamic processes, and even multiple at the same time by multiplexing. In order to achieve successful multiplexing, however, you need to choose your fluorophores very carefully in order to minimize spectral overlap. There are sources out there, such as the fpbase.org website, that can help you enter the fluorophores that you're interested in combining and calculate for you how much the excitation wavelength for one of your fluorophores could potentially also excite one of your other fluorophores if they're too close to each other in the spectrum. As an example, I put together here 3 fluorophores that are often used together in intravital imaging. The FITC that I was speaking about earlier in the green spectrum, M-cherry, which is often used to transfect cancer cells with in the red spectrum, and Alexa fluor 647, very often used to conjugate with antibodies in the far red spectrum. Now, these 3 lines represent the chosen nanometers for excitation of the fluorophores. For FITC, we typically excite with a 488 nanometer laser, and we can see that this will excite 77% of our FITC protein, but also 8% of our M-cherry. This amount is acceptable and will not cause for any problems. When exciting M-cherry with the 561 nanometer laser, we are achieving 64% excitation of M-cherry, and again an 8% excitation, but this time of the Alexa fluor. Again, acceptable. When exciting with the 633 nanometer laser, we are exciting 62% of our Alexa fluor protein and only 1% of M-cherry, which is negligible. So we can conclude that these 3 fluorophores match well together and cause for minimal spectral overlap. So we've now identified a set of fluorophores that will work well together. But how will you actually achieve separating and imaging them? That is where fluorescence microscopes come into play, and they exist of specific components to make that happen, which is a dichroic mirror and a set of filters. For intravital imaging, 2 specialized fluorescence microscopes that are most commonly used are the confocal and the two-photon microscope. They distinguish themselves from basic fluorescent microscopes by focusing a laser beam into the sample and scanning right there, point by point, rather than illuminating the whole sample at once. This is how they increase spatial resolution. In order to collect the emitted light from the illuminated scanned area, the confocal microscope makes use of a pinhole before the detector. This pinhole rejects all photons emitted from outside of the focus, as well as those that come from the focus plane but are scattered on their way to the detector. This way, only unscattered photons coming from the focal plane are able to pass through the pinhole and reach the detector and contribute to the overall signal. There's a level of inefficiency to this, though, which demands that a high laser power is used for imaging, and this could create unwanted photo damage, such as photobleaching and phototoxicity, and limits imaging depth to a maximum of 100 micron. In contrast, a two-photon microscope does not require a pinhole, since all the emitted photons contributing to the signal come only from the focal point of the excitation spot, regardless of how much they scatter on their path to the detector. Greater tissue penetration of up to 500 micron is achieved with two-photon microscopy, and fewer excitation events are required to achieve the same signal due to the improved collection efficiency, limiting potential photo damage. In order to understand why the signal in two-photon microscopy comes only from the focal point of the excitation spot, we need to have a look at the principles of two-photon microscopy, which differ from single-photon microscopy. Single-photon excitation requires the absorption of a high-energy photon to excite an electron of a fluorophore to the excited state. When this electron relaxes to its ground state, it emits a photon of light of a different wavelength than the excitation photon. In two-photon microscopy, reaching the excited state of an electron is achieved by the simultaneous absorption of two photons. Now, the likelihood for this simultaneous absorption to occur is basically only reachable in the focal point of the laser beam, which is why there is no out-of-focus fluorescence from scattered photons, eliminating the need for the pinhole. Since two lower energy photons with a long wavelength are used to create the energy needed to excite the fluorophore, penetration depth for two-photon excitation will be higher. Now let's take a moment to summarize what we've learned so far, which is that optical imaging has excellent resolution but poor penetration depth, which is linked to how light propagates through biological tissues, where it's absorbed by hemoglobin and water, affecting the penetration depth. This leaves us with an optical imaging window for in vivo optical imaging between 600 and 1000 nanometers. Here, fluorescence is the most commonly used optical technique because it's so specific and sensitive, and it allows for multiplex imaging, where you can simultaneously visualize up to 4 fluorophores when you choose them carefully to avoid spectral overlap. By now you know that intravital fluorescence microscopy can provide you with molecular and functional information at high resolution and at cellular level, as compared to some other imaging techniques that operate at a more microscopic scale. Other selling points for intravital microscopy are the fact that it can be used in situ, which is basically in the place of origin, that it provides you with spatial information, that it can be acquired in real time, and it gives you images that are quantitative. You can collect these images over time longitudinally, and this way you can also reduce the number of animals that you need in your experiment, as every animal can serve as its own control. And on top of that, information collected with intravital microscopy can provide new insights in the processes of disease staging, development, and treatment development and response. Focusing on the mouse model, where is it that we can actually apply intravital microscopy? Well, pretty much any organ, system, or structure that you can access optically, you'll be able to image with intravital microscopy. Gaining access can be done non-invasively or invasively. There are a few structures that can be accessed non-invasively, such as the ear and the eye. Pretty much every other organ and structure you want to image with microscopy, you'll need to expose surgically to be able to access it with your objective lens. You can do this by removing a skin flap and imaging your organ or structure of interest right underneath, or by extracting your organ of interest and imaging it that way. These techniques are typically not meant for repeated imaging time points and are mostly performed at endpoint only. In order to perform longitudinal imaging, imaging windows have been created, which can be implanted surgically into the tissue of the mouse over your organ or structure of interest. A few very commonly used window chambers are displayed here, such as lung chamber, dorsal skin fold chamber, mammary window chamber, abdominal window chamber, cranial window chamber, a bone window chamber, and an ovarian window chamber. A lot of these window chambers have detailed protocols that you can find in literature and that can help you guide through the creation of your own intravital model. Use these guidelines to find important details regarding imaging stability over time, imaging tolerability by the animals, and optical imaging conditions such as choosing the right cover slip thickness, typically a number 1.5, and the right field of view to be able to visualize your structures well. Nevertheless, creating your own intravital model will take a fair amount of time, dedication, and skills. Once you have established, optimized, and characterized your intravital imaging model, however, its applications are pretty much endless. You can apply it in stem cell biology, oncology, drug development, immunology, infection, and inflammation, allowing you to study cell-cell interaction, cell trafficking, cell microenvironment interaction, in vivo, and over time. When you've acquired your images, you'll want to quantify them to extract information from them that can help answer your research question. There's a vast amount of methods available, as well as softwares such as the commercially available Imaris or the freeware Imagery in Fiji, or softwares that come with a microscope. Which quantification software and methods will be best for your research? I cannot answer, but I can give you some examples of common quantifications that can be performed. You can do these in 2D acquired images or 3D acquired images, aka volumes. For example, when looking at individual cells, you can track their motion and quantify things such as speed, acceleration, and track length. When looking at a group of cells, you can quantify their volume in terms of area or in terms of cell count, number of cells. When you're looking at individual cells, you can also quantify their distance to each other or to a membrane or surface or any other structure. And that will allow you to analyze cellular interactions and also intracellular changes due to microenvironmental differences. Besides analyzing cells in your image, you can also analyze structures such as vessels. For example, you can look at how leaky they are in terms of angiogenesis or vascular damage. But you can also quantify their overall area and density, the number of branches that they have, their length, and their volume. You can also analyze both cells and vessels or other structures such as lymph nodes, and look at how cells intra or extravasate from these structures. While you're imaging, you may encounter some artifacts that are caused by motion of your organ of interest. Obviously, some organs will cause more motion than others. Here, for example, the lung will move quite a fair bit in and out of your field of view as you are acquiring your images. When you click snap to acquire that shot, you would probably most likely end up with a very blurry image that has a very poor contrast, and you'll have difficulties performing good quantification on them. So for images like these, it could be necessary that you perform a step in between post-processing quantification and image acquisition, so in pre-processing, in order to compensate and correct for these motion artifacts to get a nice crisp image that will be better suited for quantification. So from this, we can conclude that in order to perform successful intravital imaging and quantification, you need to choose the system that best fits your needs. You need to optimize your animal model in order to be able to perform longitudinal imaging. And you need to ensure good imaging quality of your window chamber. As you're acquiring your images, you need to make sure you position your animal well in respect to the objective lens, and that you have maintained its breathing rate very stably to help with reducing motion artifacts. And as you're choosing your imaging parameters to acquire your images, you need to make sure that you can keep these consistent across imaging time point and between animals in order to be able to objectively compare acquired images against each other. And as you've acquired your images, you can perform pre-processing corrections such as motion correction to optimize the image that you've acquired for quantification in post-processing. This was a brief summary of intravital imaging, and if you would like to have a more in-depth understanding of some of the principles discussed here and you missed last month's webinar, please go to the Scintica website and find it under past webinars. So now let's keep all of the things we've learned about intravital microscopy and animal models and image acquisition in the back of our mind as we learn more about how the IVM systems came about and what they are capable of. The team at IVIM Technology are definitely no strangers to intravital imaging, and have been publishing in this field for over 10 years now. Meanwhile, gaining more and more experience in microscopy, animal models, window chambers, and applying this in various applications. What they've realized along the way, and what every user using intravital microscopy in their research will realize, is that there's no easy solution to doing intravital imaging with a conventional confocal or two-photon microscope. As they're not optimized for in vivo imaging, you need to optimize every single step of the way yourself. And this is not just the access to the microscope in order to position your animal correctly and keep it anesthetized, keep it warm for your experiments. But this is also how to best acquire the images, how to best process images, because you're dealing with motion artifacts, which you would not have with stained slides. And as we discussed earlier, you also need to spend time in creating your animal model and imaging window chamber that is stable enough for you to even be able to do in vivo imaging over time. So eventually, the fact that these microscopes are not optimized for in vivo imaging makes it hard to standardize your experiments and leads to a low performance and reproducibility. To overcome these challenges, the IVM Tech team has developed their own intravital microscope, and now they're sharing it with you. It is a all-in-one intravital confocal two-photon microscopy system that is fully optimized for in vivo imaging. The company was founded in 2017 as a spin-off of the Korea Advanced Institute of Science and Technology, and has since then completed development of 4 different intravital microscopy models, and has done several installations of these models, the most recent one being at the Harvard Medical School in Boston. Recently, Scintica has teamed up with IVM Technology to help them sell the product at a more worldwide scale. The fact that these all-in-one intravital microscopes come delivered as a single box package gives them a very small footprint and allows for their easy installation, operation, and maintenance in virtually any lab space. The microscopes are also co-optimized with both hardware and software that allow for superb intravital imaging performance, such as an integrated platform for live animal maintenance, such as various imaging chambers, so that there's virtually no limitation in the amount of various organs that you can image. Also allows for ultra-fast imaging speeds, and there's live tissue motion compensation as you're acquiring your images. The product line consists of 4 different microscopes. There's the confocal only, two-photon only, confocal and two-photon combined, or the two-photon smart version that uses a fixed laser at 940 nanometers. The confocal microscopes, as I explained earlier, have a pinhole in front of their detector that allows them to reject any fluorescent signal that is not obtained from the focal plane. And this leads to images that are of high contrast with low background. So these are of good quality for analysis. And if you combine those with ultrafast, precise raster scanning and multicolor excitation laser beams, then you're able to reach video rate imaging of fast cellular level dynamics. And you can do so with a high sensitivity and using multiple colors to image multiple processes together in vivo tissue. Two-photon microscopes don't use a pinhole, but instead collect all the fluorescent signal that comes from the focal point. They can do this because it takes 2 photons in order to excite one fluorophore, and this is a very specific process, typically only limited to the focal point. So by using 2 photons at a longer wavelength, you're able to perform deeper tissue imaging. This technique also allows for label-free imaging, such as second harmonic generation. And at the same time, by using these lower energy photons, you're reducing your chance of photo bleaching or photo damage at the non-focal plane level. So making this technique ideal for long-term intravital imaging of tissues. The basis of each model is the same in terms of hardware and software. They all carry a polygonal mirror and a galvano scanner. The imaging heads can carry up to 6 objectives and reach the same field of view. And then the software is able to reach imaging speeds of up to 100 frames per second at 512 by 512 resolution, and is able to perform the real-time motion correction that I'll explain later in more detail. They mainly differ in which lasers and detectors are built into the system. With these filters and detectors, the systems are able to image a large range of fluorophores ranging from blue to far red dyes, and allowing for the simultaneous imaging of up to 4 fluorophores. Here's a video that will show some of these components inside the system. And here we take a closer look at some of these components, such as the scanner and the laser beam pads. Now we'll have a look at some of these components and discuss what makes them stand out, such as the rotating polygonal mirror that allows for ultra-fast uniform laser beam scanning, reaching speeds, as I said before, of up to 100 frames per second at 512 by 512 pixels. Using this polygonal scanner, you're able to achieve a uniform excitation illumination over your entire field of view. So that means that there will be no reduced fluorescent signal or signal to noise ratio at the center of your field of view. There will be no excessive photo bleaching at the edges of your field of view. And you'll achieve a uniform high signal-to-noise ratio over the entire field of view, overall leading to an improved image quality without you wasting any excessive photons. Another unique feature of the system is that it comes equipped with a sliding blackout curtain. So here in this opening, you see the platform with the animal positioned underneath the objective lens. You need this axis to place your animal there and make sure that everything is set up right for you to acquire images. But once you're ready to image, you don't want any polluting ambient light accessing your detectors and affecting your image quality. So typically you would make sure that that doesn't happen by turning off all unnecessary lights in your room and by surrounding yourself with blackout curtains running from the ceiling to the floor. Here in this case, you can just close the curtain that is right here in the system, um, blocking all light from coming in as you're acquiring your images. Now let's have a closer look at the platform. The platform is integrated into the stage in the microscope, but you can also detach it and take it to your lab bench where you want to do your animal manipulations and positioning. Within the platform is a body plate heater that can keep your animal nice and warm. By using a rectal probe, there will be a feedback that goes back to the control system that will adjust the temperature of the plate heater to the need of your body, of your animal's body heat. If you want to image an organ that you remove from the mouse at the platform, you can use a imaging tissue temperature heater where the glass cover slip will be heated to the animal's body temperature while you're imaging it. You can also equip your platform with gas anesthesia connection of your choice, and the connector tubes, they will feed into the system through openings at the side of the box that are also fully light-proof. Once you're ready with your animal manipulations and positioning, you can take the platform back to the stage and place it on the stage holder. There, that one you can extract from the system for easy access and then slide back into place. That whole stage can be moved along the X, Y, and Z axes so that you can position your mouse in a way that is optimal for you to be able to image your organ of interest. And connected to the stage are all the different connectors that you need to connect to the heating plate and to the anesthesia system if using one. With some window chamber models, such as the cranial one here, it's not always enough to adjust your stage according to the XYZ coordinates in order to have a nice level imaging plane to your objective lens. Because of some curvature that's going on, you may want to actually adjust your lens head along XYZ axes and rotate them until you have found your optimal imaging plane regarding the structure that you want to image. So this is a possibility that that can be offered with the IVM Tech systems. And this video here shows you the range of motion of this rotational objective lens head. In the acquisition software, you'll find the majority of the features that you will also find in other softwares, such as acquiring a Z-stack, where you, as shown in the left hand video, can acquire an image at multiple images at multiple levels and put those all back together into a 3D volume, as shown on the right. You can also acquire a time-lapse image if you want to study a dynamic cellular or a vascular process over a certain amount of time. And if you want to increase your field of view, you can also take multiple images in the same plane within a larger area and then stitch those back together. What you won't find in the majority of the acquisition softwares, though, is the ability to compensate in real time for motion in your images coming from animal breathing. The IVM tech team has integrated this into their software because they know how important it is to acquire a crisp, sharp, in focus image rather than a blurry, out of focus image. That will complicate post processing analysis, but also just not look great um, on publications. And yes, you can take a pre-processing step in between acquisition and analysis using a different software to yourself compensate for animal motion, but this will just take additional time and need an additional software. Um, Now, in the IVM Technologies acquisition software, all you need to do is acquire a short video so that the software has enough information about where structures are supposed to be, and so that they can be tracked. And when you um, acquire that video, it can later be processed into a single image that has where the positioning of these different structures has been kind of recreated, leading to a sharpened, motion compensated image. The example shown in the previous slide was the heart, which is obviously one of the fastest moving organs, but many other organs you'll find also suffer from motion that you just really can't avoid, such as the liver. And in case you would just snap a picture without any correction, you would often end up with a very blurry image as shown here. But then with motion compensation, your image comes out nice and sharp. And yet another example here for the lung, which shows different type of motion, again in a different type of direction. But also here, you can clearly see how taking an image with the motion compensation does not suffer from any motion artifacts that you would otherwise have with, without the compensation. I hope I was able to showcase the unique features that the all-in-one intravital microscope from IVM Technology brings to the table. I'll summarize those in the next slides, but I just want to point out that besides offering 4 different models optimized for intravital imaging, the IVM Technology team can also work with you to customize their systems in order to meet your specific needs, such as the rotational lens head that I've shown. And besides the fact that they already offer a wide range of optimized imaging window chambers that are fully compatible with their system, also here is room for additional customization and for them to create imaging window chambers with you, or to make adjustments to your existing ones in order to be fully compatible with their system. And then if you're unsure if intravital imaging is feasible for your specific application or specific model, you can work with them as they have many, many years of experience in order to try to answer that initial research question, that initial question you may have regarding your research being compatible with intravital microscopy. Before I show you some really cool images, I want to just summarize what I've shown you so far, which is that I've introduced you to the first all-in-one confocal and our two-photon microscope optimized for in vivo imaging. I've shown you that they have a very small footprint with easy installation and integration into any lab space, and that they're equipped with a superb live animal maintenance platform and ultra-fast scanner, and furthermore optimized to image a great variety of internal organs while being capable of real-time motion compensation. I will now be showing you some images acquired with the IVM confocal microscope, ranging over a few key research applications. In general, intravital microscopy is most widely used to study oncology and immunology, to research drug development in stem cell biology, And there's also really good models out there to study inflammation and infection with intravital microscopy. Then often using the um, zebrafish or the fruit fly animal models. Developmental biology and regeneration is being studied with intravital microscopy. And then more recently, applications are emerging for the study of tissue engineering and microbiology. We'll start with some examples in oncology. The dorsal skin fold chamber is one of the best characterized chambers out there and has been used extensively in oncological research. You can compare it a little bit to a subcutaneous tumor model, as it's not quite in situ growth of cancer cells unless you're studying skin cancer, but it has allowed for a lot of interesting research and progress in terms of oncological development and treatment response. So here you see an example of a dorsal skin fold with a nice vessel structure through it. When you take an image with the confocal microscope after having injected some dextran to light up the vessels and after having injected some cancer cells and allowed some time to grow, you can visualize these as red and green respectively. If you want to zoom in a little bit more into this area, you can distinguish microcapillaries as well and start to see more individual cell structures. So in this model specifically, we're looking at human non-small cell lung carcinoma. And what this system will allow us to do is to basically track changes in tumor growth over time or changes in vessel structure over time. So this is shown here, images taken at day 7, 10, and 13 after a treatment regimen that instead of targeting the cancer cells is targeting the newly formed vessels that are supplying supplying the cancer cells with nutrients. So after applying this anti-angiogenic treatment and identifying your field of view that you want to track over time based on a vessel structure that is easily recognizable at each imaging time point, you can basically go ahead and track changes in green and red, being changes in the number of cancer cells or area or volume of cancer cells, and also changes in vessel morphology and dilation. Using the same window chamber model, you can also evaluate the treatment that targets the cancer cells directly, such as one delivered in nanoparticles. Even though they are very small, they can be visualized with confocal microscopy. Here, they're labeled with a red fluorophore and are shown against green labeled human triple negative breast cancer cells and far red labeled anti-CD31 antibody. This antibody labels the endothelial cells of the blood vessels and is here given the pseudo color of blue. That's not the light that is being emitted from the fluorophore. So here is evaluated how the nanoparticles, after injection into the bloodstream, reach the tumor and extravasate from the blood vessel to infiltrate the tumor site and start treatment. Multiple time points are collected, but here within the first 24 hours after injection. You can not very well appreciate how many red nanoparticles are present and where they're located because of the green cancer cells that are larger and brighter, as well as the nanoparticles. So in order to visually appreciate where the nanoparticles are at and how many there are, we can simply remove the green channel from the other ones and only look at the red and the far red channel. That way you can appreciate that indeed there are more nanoparticles entering and extravasating from the bloodstream and accessing the tumor site. Of course, when you're analyzing this image, you would analyze every channel separately. So this is just a tip for visualization purposes. Another commonly used window chamber model to study disease and drug development is the abdominal window chamber. As you can see here, this is typically a circular chamber with a cover slip of about 8 millimeters, and it will allow you access to any abdominal structure that you're interested in. Here, spleen, kidney, and pancreas are visualized all together. And also worth noting is that this window chamber slides right into this holder that is attached to the imaging platform of the IVM microscope, so helping you stabilize and position your animal. A few images taken through this optical imaging window chamber showing islet beta cells in the kidney and the pancreas surrounded by vasculature, or showing monocytes and dendritic cells moving in the spleen, also surrounded by vasculature. The mice used here are transgenic mice, which means that they have been modified in such a way genetically that they will endogenously express GFP for these specific cells here. You can also perform gastric imaging with this type of window chamber and access small and large intestine. For example, here we're looking at colon cancer implanted into the cecum in green and vessels in red. So as you magnify closer into the tumor, you see that it's made up out of individual cells, but it's like a tight-knit community sitting in a nest of vessels that are providing nutrients to it in order to survive and grow. Removing the green channel, you can see just the vessels here. You can appreciate how unstructured they are. They're poorly formed, probably leaky vessels that were just quickly formed in order to supply the tumor of nutrients. Another organ worth investigating in the abdominal region is the liver. In this work, the pathophysiological drivers of non-alcoholic fatty liver disease were studied. This disease is chronic and affects people worldwide. However, its mechanistical drivers have not really been understood yet, so therefore effective treatment strategy has not yet been established. In this work, researchers developed a novel fluorescent lipid droplet labeling dye, the SUO-Fluor-44 or SF44, in order to visualize individual lipid droplets. They combined this with an anti-CD31 far-red antibody to visualize vasculature, and were able simultaneously, and were able to establish a spatial distribution of hepatic lipid droplets in a mouse model that was put on a high fat diet to recreate the chronic fatty liver disease. So by performing repeated intravital imaging in this model, as it was on this high-fat diet, the researchers were able to showcase that these yellow hepatic lipid droplets over time on this diet were growing in size. And compared to the normal diet, they were definitely more prominent. There's also an abundance of immunology research studies using intravital microscopy. In order to study an immunological response, researchers here used the ear window chamber model. In fact, there's no window needed here, nor surgical manipulation, so it's one of the easier models to employ. The skin is just thin enough to be able to image right through with confocal microscopy. The research has used a lysosome M GFP model to study their immunological response in, because this model expresses a GFP in the lysosome M enzyme, which is primarily excreted by neutrophils and macrophages. Here on the right in this video, you can basically see the green cells move, which are the neutrophils and the macrophages, and you can see their location against the vessel structure, labeled with a anti-CD31 antibody conjugated with a far red fluorophore. So this mouse window chamber model was then used by the researchers to study the immunological response to the CARS protein, which has previously been shown to be secreted from cancer cells, where it then induces inflammation. In this study, the CARS protein was labeled with a far red fluorophore and injected intradermally into the ear. And then a time-lapse video was made over the next 6 hours, imaging the same region and tracking the recruitment of neutrophils and macrophages to the site of injury. As you can see, over time, more and more immune cells are being recruited, and they're populating the site of injury. Other popular immune cells to study are, of course, the T cells and the B cells. And without going into too much detail about the background of this study, I wanted to show you this video where you can appreciate T and B cells extravasating and intravasating from this lymph node in the hind leg, and allowing you to, over time, basically track their movements and population. Another application is in stem cell biology. For example, bone marrow transplantations, which are widely used in patients with blood disorders and cancers, can be studied using intravital imaging. You can do so in the bone marrow of long bones, such as the femur, for which there are also window chambers. But more commonly, the calvareal bone in the skull is used because it's easier to access. And there's plenty of bone marrow to be studied there as well. So as you can see here, the skull is exposed, and a cover glass is placed over it that allows for optical imaging of the calvareal bone, and you can nicely see all of the large veins and the sutures running through this. On the right are some longitudinal wide area confocal images of this same bone. You can kind of recognize the structures up here, and what is imaged is our bone marrow cells transplanted from one mouse into the other and tracked over 4 days since transplantation. So the researchers were able to see an increase in transplanted bone marrow cells from day 1 after transplantation up to day 4 after transplantation, where cells were not only increasing in number, but they were also distributing more widely across the bone marrow, and they were forming clusters that were also increasing over time. They also collected a video to observe proliferation events during a 5-hour time lapse. So arrows point towards transplanted bone marrow cells that are undergoing proliferation, which of course contributes to this increase in the number of cells and clusters that can be seen over time after transplantation. Studying infection is also important, especially in this day and age of COVID-19. A good place to study such an infection would be in the lung. Now, a lung chamber is not your typical window imaging chamber. It requires a bit more of an advanced setup because you can't just place the chamber over an exposed lung. It would deflate and your mouse would stop breathing. So you'll need to intubate your mouse before you can do imaging. And as you're performing imaging, as you can see in this video on the right, you'll need to basically suck the lung up against the glass so that it's stabilized and inflated. And this will not only help with the imaging, but also with the mouse breathing. For example, by imaging red-labeled neutrophils in the pulmonary microcirculation, you can evaluate the level of sepsis in the lung. You could also interest yourself in tracking red blood cells in the lung microcirculation. And in post-processing, you can then analyze the path of these red blood cells and their track length, as well as their speed, with red being faster moving to green being slower moving red blood cells. I hope I've been able to show you that intravital imaging has come a long way, and with the recent development of the all-in-one intravital microscope from IVM Technology, it's just one step closer to allowing a multitude of users to access this very exciting imaging technology. And with that, we have reached the end of this webinar. Thank you for joining us, and we hope that you have learned something about the IVM microscope and that you liked what you heard. If you want to know more about how it is being applied currently in the research world, then please do sign up for the following webinar in this series. And don't hesitate in the meanwhile to reach out with any other questions you may have.
Thank you, Sarah, for the great discussion today. We've reached the 60-minute mark for our session today, and to be respectful of everyone's time, we're going to wrap things up. As I mentioned at the start of our webinar, we will be sure to answer any questions in the written transcript, and we'll work to get this out to you over the next week or so. I'd like to thank Sarah for the wonderful presentation today, and I trust that we have been able to provide you with some relevant information about the IVIM Intravital Microscope. As I mentioned at the beginning, today's webinar was the second in what will be a 4-part series. Please keep an eye out for emails in the following weeks for the next portion of the series, or visit our website to view the previous recorded session. If in the days and weeks to come you have further questions about the modalities discussed today, I encourage you to reach out to us here at Scintica, and we will be happy to discuss further. We will welcome the opportunity to discuss your specific research goals and how any of our imaging systems could help move your work forward. Thanks again to all of you for taking time out of your day to attend our session. We look forward to seeing you at a future Scintica event. Have a great rest of your day. Thank you.